In this lecture, we are going to talk about functions with multi-variables. So we start with a function of two variables. Well, f is a function of two variables x, y. If for each pair x and y, you can find one number correspond to this pair. Okay, so the domain of this function will be in R2 because you have, the independent, you have two variables to plug in. You have x that is changing, you have y that is changing. So your domain is in R2. But the range is the set of values that f can take on, and that is still real numbers. So your range is a subset in R. Okay, so you come up with x and y, two numbers, you plug them in at the same time, and you end up with one number. We often write z equals f of xy to make explicit that the value taken on by f at the general point xy, as in, x and y are the independent variables that we plug in the formula, and then z is the dependent variable. Okay, so these are, well, pretty much the setup of a function that starts with R2, or maybe a subset of R2. Then the output is still one number. You might want to think about the vector functions. They are sort of backward. Vector functions, you have one vector, you have one independent variable t. Then you end up with 2-3 components. You have x, y, z, right? So each t will give you an x and y and a z. So each t will give you sort of 3 real numbers at the same time. This is like backward, but not inverse, okay? This is like a backward. You start from like a bigger set. You start from a bunch of variables, but they all contribute in the formula to give you one real number. For example, our f of xy is square root of y minus x squared over 1 minus x squared. So this is a function of two variables x and y. And if I want to evaluate f of 0, 2, pretty much x equals 0 and y equals 2. Okay, so you plug in x equals 0 and y equals 2 at the same time. F of 0, 2 will be square root of y is 2 and x is 0 over 1 minus x is 0. So you have square root of 2 over 1, which is square root of 2. Well, when you have two variables working together to give you the value, it is sometimes harder to tell how the function really works. You can, of course, point by point, you can sort of get a number, but it's harder to sort of like sense how the independent variables cooperate together, other than this formula that you've seen. Which makes the following question sometimes hard. Well, find and sketch the domain of f. Well, the finding part actually is okay, in the sense we're still following the same rule as regular finding domains of functions. We just need to make sure every part of the function works, which means if you have a square root or in general even root, the radicand can't be negative. And when you have a denominator, the denominator can't be 0. If you have a function that asks for a particular domain of value, say if you are putting something in log, you need to make sure the input of log are positive. And if you have, say, sine inverse or cosine inverse, you need to make sure the input of your sine inverse and cosine inverse has to be between 1 and -1. Okay, so in particular, here our function has a square root. So we need the square root to be greater than or equal to 0. We need the radicand of the square root to be non-negative. And also we have a denominator. We need to make sure the denominator is not 0. So in order to make our formula of the function work, we have two conditions. The radicand can't be negative and the denominator can't be 0. And this is an AND, okay? Both of them has to be true. Then you just solve them together, well, one by one. Not together, sorry, one by one. So y is 1 minus x squared is greater than or equal to 0. That means y is greater than or equal to x squared. And 1 minus x squared is not equal to 0. That means x squared is not 1. So the first one I can't really solve anymore. Sorry, the other way. Y is greater than or equal to x squared. The second one I have x is not positive or negative 1. So putting these two conditions together in a domain set notation, we know that the domain are the pair of real numbers x, y such that the two conditions, which are y is greater than or equal to x squared, and, comma means and, x is not equal to plus or minus 1. This is the domain. Okay, we write domain in set notation. This is set notation. Your domain is a set of all the possible ordered pair of x, y values. Now sketch the domain. Your domain is in R2, so the graph of domain will sit in R2. And what we have in R2? First of all, we have y is greater than or equal to x squared. So we first draw the boundary function. I think that's enough. I'm having y equals x squared, so the parabola. I'm going to really plot the points, and then I draw my parabola. I have this is the y is equal to x squared. Now my y is equal to this, which means that's why I'm drawing the solid line. Solid line means included, and dotted line means not excluded. Okay, as lines. And of course as point, included we use solid point, and open circle is excluded. Now we have the boundary and we have our point above the boundary. So pretty much inside this parabola, that's our first condition. But we say that x can't be positive or negative 1. So we are going to take away x equals negative 1 and x equals positive 1, which is this dotted line. And in particular, on the boundary, you take away the point. I take away this point and the whole line. X equals 1. That is the graph. So pretty much it's like you have the parabola, but you take away these two strings. Okay, so that's how you find and sketch the domain of a two-variable function. If f is a function of two variables, D is the domain, then the graph of the f will be, you have the domain x and y, and you also have the range or the output z. So you have three variables, x, y, and z, which means the graph of the function will be in R3. And it satisfies the equation z equals f of x, y. Okay, and also you need to make sure your x, y, the choices of x, y is in the domain. So here I'm doing a pretty easy example. Sketch the graph of the function f of x, y equals 4 minus 2x plus 2y. So first, you want a letter, explicit letter for the function. So z equals 4 minus 2x plus 2y. What kind of function is that? Do you realize it? It's a function in three variables, right? So if I put all my letters on the left, it will be 2x minus 2y plus z equals 4. Now see, it is a plane, right? So it is a plane in R3, which means I just need to graph it by finding the intercepts. 2x equals 4, negative 2y equals 4, and z equals 4 are how I find my intercepts. X equals 2, y equals negative 2, and z equals 4. So I'm having my x, y, z axes, and I'm having 2, negative 2, and 1, 2, 3, 4. So x equals 2, z equals 4, and y equals negative 2. This will be a plane on the sort of the left side of my xz plane. Okay, so this is 2, this is negative 2, and this is 4 on z, and here's my origin. This is the graph of my function. By the way, since my function has no denominator, no radical, actually the domain is the whole xy plane. So anything in the plane that I drew will be taken, because they are not bad pairs that has to be taken away from my domain. Okay, now you can pause the video and try practice number 1 through number 3. Similarly, we can define functions with more than 2 variables. For example, 3 variables or even more, right? A function f of 3 variables is a rule that assigns each ordered triple x, y, z in a domain in R3 a unique real number denoted by f of x, y, z. So this time you need 3 numbers together to give you the real number, the value of the function. Again, here I give you an example. Well, this is again pretty complicated one, but all you need to do is say, okay, when I'm evaluating my function f of 1, 1, 1, that's my x, y, z. So I know that x equals 1, y equals 1, and z equals 1, and I plug them in. So f of 1, 1, 1 will be square root of 1 plus square root of 1 plus square root of 1 plus log 4 minus 1 squared minus 1 squared minus 1 squared. Of course, here I'm trying to make it easier by saying they're all 1, so don't worry too much about which letter is which. Then you evaluate, what you get? You have 1 for square root of 1, 3 times, plus log 4, take away 1, take away 1, take away 1, so you have log 1, which is 0. So the whole thing is 3. The value of the function is 3. Now, the second part, I'm not asking you to graph the function, but graph the domain, but I do ask you to find the domain of f. Well, to find the domain of f, again, what you need to worry about is all these square roots, they have to be, well, the radicands have to be non-negative. So for each of the square roots, you need the inside, the radicand, to be greater than or equal to 0. So I have x greater than or equal to 0, y greater than or equal to 0, also z greater than or equal to 0. Then I have a log. The input of my log has to be non-negative. Well, no, have to be positive. I can't take 0. So this have to be greater than 0. And these are the conditions I need to make my formula work. The first 3 is already explicit, so I'll leave them here. The third one, I'm going to, well, I'll do it here. X squared minus y squared minus z squared. I move my 4 to the right hand side and then divide by negative 1. Okay, so I'm going to have x squared plus y squared plus z squared is less than 4. because when you divide by a negative number, you need to change the sign of the inequality. So what you really have, first of all, let me write down my domain. My domain will be the triple. By the way, this part is very important. This part tells you like which space you are in, your domain is in. Is it in R2? Is it in R3? So you need to write it. Okay? You need to know, okay, the domain are triples of numbers, okay, instead of doubles of numbers, or maybe there's a missing, I don't know, t that, doesn't really matter, but it is one independent variable. That is possible, right? So you need to tell like your domain sits in which dimension in a way. Okay, so I need a triple to satisfy x greater than or equal to 0, y greater than or equal to 0, z greater than or equal to 0, but meanwhile x squared plus y squared plus z squared is less than 4. Okay, that's our domain. Again, I'm not asking you to draw it, but this is a sphere, or a ball. It's a solid ball, right? X minus 0 plus y minus x minus 0 squared plus y minus 0 squared plus z minus 0 squared is less than 2 squared. So what you really have is a ball with diameter 2. And then you are taking sort of the part that everything is positive. Okay, so it's like I can't really draw it, but it's like in the front sort of corner, okay, of it. So you are having, if you imagine this is like an orange, although I don't think anybody cut orange this way. So you are like slicing your orange into like 8 pieces, so it's like, this is, first you slide it into 2 and then you do this, and then you do this. Okay, and the part that everything is positive, that piece that everything is positive in that corner is the domain. But anyway, I'm not asking you to graph it, so don't worry too much about the graphing. You don't need this. Okay, it's almost, impossible to really draw by hand. Okay, the last thing is that level curves. The level curves of a function f of 2 variables are the curves with equations f of xy equals k, where k is a constant. So when you are having multivariable functions, the graph of the functions is in a higher dimension, like it's in 3-dimensional. Again, it's about our resource. What we are drawing in is 2-dimensional, so it's very hard to draw 3-dimensional objects on a piece of paper. That is why it's important to have a way to make it happen in 2-dimensional. That's why we have these level curves. Okay, and the level curve is all the points. A level curve f of x y equals k is all the points that give you a value k. So one of the common example which I show here is that when you go to, say, the mountains, when you are hiking, they have this picture and showing with like little, curvy loops, right? So one common example of level curves occur in topographic maps of mountainous regions. So here, level of curves are really the curves of constant elevation above the sea level. So it's like, if you walk along the curves here, that they show you, you are not going any upward or downward. It's like you walk steady, like on the same height. if there's a path, of course. But this is a way they sort of tell you at each xy coordinate on our plane, Earth. Although, of course, we are only having a very, very small piece of Earth, part of Earth, so we can imagine its plane because you are having a huge, the ball has a huge diameter. So in comparison, you can imagine it's flat. So on each coordinate, what is the height of that particular place of Earth? So that's a way you can show three-dimensional objects, giving three-dimensional information in two-dimensional space, or in two-dimensional, I don't know, what's the word? Graph. Okay. Now, last example for today, we are going to do a baby version of the level curves. So here we are going to sketch the level curves of function square root of 9 minus x squared minus y squared. And we are going to find the level curves for k equals 0, k equals 1, k equals 2, and k equals 3. So when k equals 0, you are having square root of 9 minus x squared minus y squared equals 0. Square both hand sides. 9 minus x squared minus y squared equals 0. And then you can imagine you move both of them to the other side and switch. So I'm having x squared plus y squared equals 9. K equals 1. I'm having the same thing. The formula equals 1. Square both hand sides. I'm having 9 minus x squared minus y squared equals 1 squared. Again, 1. Now, minus 1 on both hand sides. Move my x squared and y squared to the right. But write it first. I'm having x squared plus y squared equals 9 minus 1, which is 8. Now, k equals 2. I'm having square root of 9 minus x squared minus y squared equals 2. Square both hand sides. I'm having 9 minus x squared minus y squared equals 4. So similarly, I'm having x squared plus y squared equals 9 minus 4, which is 5. Finally, when k equals 3, I'm having square root of 9 minus x squared minus y squared equals 3. Square both hand sides. 9 minus x squared minus y squared equals 9. 9 minus 9 give me 0. Okay, these are all circles with diameter 3 to radical 2, which will be 2.8-ish. This is square root of 5. I don't have better ways of writing it. Square root of 5 will be sort of 2.4. 24 squared to 496. So yeah, close there. And this is, of course, 0 squared. Then I'm having my domain in xy space. So 2 axes. I'm having 1, 2, 3. 1, 2, 3. This will be so hard to draw with hand. So this is k equals 3. But good thing is I have different colors. Let's do blue. This will be 2.8. So it will be almost the same place. A little bit thinner. Smaller circle, but it's hard to draw circle inside circle. So this is k equals, oh sorry, the previous one was k equals 0. My bad. So this is 0, and now I'm having k equals 1. Now next I'm having k equals 2 at what? Square root of 5, so it's like 2.4-ish. That's a little bit too small for 2.4, but yeah, I can't draw the third circle anymore. Like, the more circle you draw, the the worse reference you are having, so they are like less and less round. This is k equals 2, red. And finally, k equals 3, you have just 0, nothing else. So I don't know, gray, can we see it? K equals 3. Okay, these are the level curves of our function, and what they represent is the z value. So on the purple circle, all of the z coordinate is 0, and on the teal circle, all z value is 1. On the red circle, the all z value is 2, and at the point, the z value actually is 3. So if you can imagine, you pull the circle, like if you hold that gray dot and pull it away from the xy plane and get each of the circles to their height, which means the purple with height 0 remains on your xy plane, and the teal gets a little bit higher, and the red gets even more higher, and finally the gray gets height 3, which is like on the top. You get this, where I have my purple like on the ground, and I have my teal with height 1, so it will be somewhere like here, and then I have the red with height 2. Oops. And finally, I have my gray at the tip. Okay, so the graph of the function actually can be sort of recovered from your level curves. You are having the graph of function, which is a semicircle, the upper half semicircle with, not semicircle, semisphere. Well, yeah, that's my first remark. The graph of the function actually is a semisphere, the upper half of the sphere, which is the surface of a ball, with center at the origin and radius 3. And if you look at functions of 3 variables, then you will not have level curves. Instead, you will have level surfaces, where you get level surfaces by deciding what the output value is. So essentially, you are having an equation with f of x, y, z, 3 variables equals a number. You are in R3, and the equation itself take away a dimension. You have two dimension left. That's why what you will have are level surfaces, which I'm not going to make you to draw. But just be aware, when you have actual variable, you get actual dimension, as always. Okay, now you can finish your practice number 4 and number 5.